Hi everybody, my name is Matteo Vincenzi and I'm a researcher at Equador Informatica. At the same time, I'm carrying out my PhD at the Technical University of Catalonia within the framework of a European H2020 project named 5G Aura. This presentation will describe the results of my first work and publication titled Cooperation Incentives for Multi-Operator C-RAN Energy Efficient Sharing, which has been presented at the IEEE ICC 2017 conference in Paris. I will start with the introduction of motivations and contributions and then move to the description of the system model and of the cooperative game used for solving this problem. And finally, I will talk about the performance evaluation and conclude the presentation. The main motivations of this work are the mobile data traffic explosion experienced in the last decades due to both the device increase in number and the arising of many bandwidth greedy applications. At the same time, another problem to be solved is the scarcity of the spectrum resource. So to address these problems, mainly an enhancement in the infrastructure can be introduced in order to better utilize the spectrum resources by implementing dense heterogeneous networks, which are spectrum efficient, but they have the drawback of having high costs. So this infrastructure enhancement by itself is not sustainable for achieving 5G perspectives and goals. Therefore, a new architecture called centralized radio access network has been proposed for centralizing the baseband units, which are those components of the base station related with the computational part of the base station itself, and centralizing these units in the same position in order to first share the cooling and hiring cost of the assets, and at the same time this would provide global knowledge of the network state, so being able to implement more appropriate optimization strategies on our radio access network. While at the antenna side we keep the remote radio heads, which are electronic devices only used for the transmission and reception of the signals. The drawback of this strategy is still a high capital expenditure, since we would use special purpose hardware at the BBU side, although we have some advantage due to the centralization. So an evolution of these technologies known as Cloud RAN, they are very similar. The only difference is that the BBUs, the centralized BBUs, are implemented by means of general purpose processors. So we use commodity off-the-shelf hardware, which is much cheaper, and so we can conserve the advantages of the centralized RAN architecture, and at the same time further reduce the costs for the deployment of this architecture. And so we can also jointly optimize the multiple cell coordination from a centralized place with a flexible strategies, and in this way exploit the multiplexing diversity which we can have in different cells and different times. Let's make an example. If for traditional networks all the BBUs would be always active all the time without any dependence on the traffic fluctuation, with the Cloud RAN we can switch off some BBUs represented here in red and keep only a portion of them represented here in green color, And so we can see how the Cloud Run power consumption can actually follow the trend of the traffic fluctuations. And so we have a scalable radio access network which is spectrum and energy efficient. So this kind of infrastructure enhancement solves part of the problem, but still spectrum is a scarce resource. So in order to address the spectrum scarcity and enhancing the availability of it, millimeter wave have been proposed, so higher frequency which allow higher bandwidths, and for sure will be part, most probably will be part of the 5G standard. But still we would have high expenses due to the purchase of the spectrum licenses and to the research and development needed for making this new frequency commercially available. So another approach can actually be used, which is the sharing of the spectrum among the operators. So we have a problem mainly concerned with the study of providing incentives to the mobile network operators to share their networks in order to improve users' quality of service and have higher gains. Mainly we study this problem by means of coalitional game theory, and the main contribution of the work are the definition of the conditions needed for this sharing for being beneficial, and so how many and which MNOs shall share, and which can be the pricing strategy for the MNOs in order to make this sharing beneficial. And why do we talk about beneficial sharing and incentives? Because typically MNOs always try to keep a strategy, a standalone strategy where they work by themselves and try to differentiate and compete among themselves. But since we reached a point where, as we said, the spectrum is a very scarce and valuable resource, perhaps they shall consider the option of sharing, and so we provide by this study the incentives, the reasons, trying to convince them that it might be a good strategy alternative to the standalone approach. So let's introduce now the system model. We have, as we said, an heterogeneous network with a centralized architecture. So we have all the BBU pool located in the same place, and we have M operators in a given area and N UE user equipments in the same area. Each operator has got a given market share, mu m, which represents the percentage of the total number of UEs, of the total number of user subscribers owned by the particular operator M. And each operator deployed its own heterogeneous network CRAN with small cell architecture, and will own a given bandwidth license over a bandwidth BM, and we consider remote radio heads distributed according to a uniform distribution, and each operator has got UM BBU servers, and this number can vary. These numbers can vary for each operator. As well, we model the user activity through an activity factor FA, saying that the user will be active with a certain percentage of time and idle during the rest of the time. And we consider a proportional fairness scheduling, meaning that every user will be treated at the same time and provided with the same number of resources, independently from its belonging to a specific operator. So in a given small cell area, each remote radio head would serve every user equipment connected to that specific remote radio head with the same number of resources, independently from if this user equipment belong to an MNO an MNO rather than another one. So let's now introduce the cooperative game. First, we define the standalone approach. As we said, is the approach according to which each operator actuates alone. So we model the revenue of the operator as rho m, which is proportional to the user tariff applied to the user subscribers for a given service required, we have the revenue proportional also to the quality of service guaranteed to the user. So in this case we consider it as the guaranteed data rate. And also the total revenue of the operator would depend, of course, on the total number of user subscribers owned by the operator, while the cost would be mainly the total number of power consumed by the operator for maintaining the operation of its own network multiplied by the cost of the electricity, and the profit is just the subtraction of these two terms, revenue minus costs. In the cooperative approach, we can have multiple operators deciding to share their own networks, and so if we name a given coalition as omega, the value of that coalition would be the sum of the revenues of each operator in that coalition minus the total cost of the for maintaining the coalition CRAN. So we consider a fair cost allocation among the operators, and so in other words we consider that the portion of the total cost paid by each operator is proportional to its market share. So they will pay a portion of the total cost of the power consumed proportional to the total number of users they own in that area. Let's now define the difference among ground coalition and sub-coalition. The ground coalition mainly is the coalition formed by all the players in the game, while sub-coalition are whichever other set of coalition formed by a smaller number of players in the area. So by these definitions, the core can be defined as the set of the cost allocations such that all players prefer the ground coalition to the sub-coalition. So there doesn't exist any sub-coalition which provides a better payoff to its players rather than the ground coalition. So the objective of the study is verifying the conditions for the sharing of among the players to be beneficial and for the core existence. We built a custom simulator in MATLAB where we consider mainly two scenarios. In both of the scenarios we analyze the case with three MNOs in the considered area, and in scenario A every operator has got the same bandwidth of 20 megahertz, has got a spectrum license over a bandwidth of 20 megahertz, while in scenario B the bandwidth is for operator 1 5 megahertz, for operator 2 15, and for operator 3 20 megahertz. And and the market share in the first scenario is equal for each operator, so they own 1/3 each of the total number of user subscribers, while in the in scenario B it is proportional to the bandwidth owned by the operators. So let's analyze the case of scenario B. First of all, we provide the offered data rate in the different approaches. As we can see, we highlighted the rate offered in the standalone case in the y-axis, and in the x-axis we have the offloading factor of provided by this specific strategy. The offloading factor mainly is the portion of the total number of user subscribers offloaded to the small cell layer, and so served by the remote radio heads of the small cell remote radio heads of this heterogeneous network. So the higher the offloading factor, and the better would be the coverage by the small cell layer. So as we can see, we are in the lower left corner when we consider the standalone approach. While if we consider sub-coalition, we have both a coverage and offer data rate increase. So with sub-coalition of two MNOs, the data rate increases, the offloading factor increases, and as we said, the revenue will increase also because it's proportional to the guaranteed quality of service. And this is mainly justified by the fact that the network pooling optimizes the spectrum usage. And if we consider a ground collision, we have the best performing case with a higher offered data rate and very good coverage. While considering the coalition's payoffs, introducing the evaluation of the revenues versus the costs, as we can see from this plot, we have in the y-axis the value of coalition omega, and the x-axis the tariff applied by operators to their users. And so for having positive profits, a minimum tariff has to be applied. So this means that mainly this is the tariff needed for revenues covering the costs of the coalition. And if we move to the sub-coalition consideration, we always perform better because, as we said, we offer high rates, and so we achieve higher revenues, but at the same time the cost increase is negligible. While in the case of the ground coalition, we still have higher rates, but the cost increase is not negligible, so we would have to set a minimum tariff higher than the one needed by the standalone or the sub-coalition approach. And so this is mainly justified by the fact that the bigger bandwidth over the pool infrastructure requires higher costs, which cannot be neglected. So some remarks: cooperation is always beneficial, but in the coalition choice, the target tariff by the operators, so the tariff the operator would like to charge, is very important for defining whether we shall choose a sub-coalition or the grand coalition. For example, if the operator wants to keep cheap tariffs, perhaps sub-coalition are better, while if the operators are targeting business users, perhaps ground coalition is good, because it is true that we will have to set a higher tariff, but the user would be willing to pay it for having a much higher rate. In this general scenario B, we can also choose pick among the different sub-coalitions, as they will provide different profit opportunities. Let's now focus on the core existence, and so the portion of the costs that operators are willing to pay, which, as we said, is the core definition, and for the ground coalition to be the best option. We are representing in this plot, in the x-axis, the portion of the cost paid by operator 1 that operator 1 accepts to pay. In the y-axis, the cost that the operator 2 accepts to pay, and then the portion of the cost that operator 3 is willing to pay is just 1 minus the sum of the portion of the cost paid by the other two operators. So by fixing a specific tariff, which we represent with tau r, in this case is equal to 0.62, we have represented with the black color the unstable ground collision, so all the combination of cost allocation which make the ground collision being not the best option. The ground collision doesn't provide higher profit than the sub-collision, and so in that black area mainly the core doesn't exist, and we represent with the white star the market share of the operators. So this tariff 0.62 is the minimum tariff for the ground collision to be stable, or in other words for the core to exist. And in particular, as we can see, the market share is the only acceptable solution, as it always belongs to the core. And we'll see it now, because if we increase the tariff, now we have it set to 0.71, the star still belongs to the region, represented here with the gray color, which mainly represents the cost allocation within the core. So the set of all the cost allocation which make the ground collision stable and performing better than the sub-collision. So the market share is still within the core region. And this means that by increasing the tariff, MNOs can accept a wider range of cost allocation. And we can see it by further increasing the tariff up to an extreme case where actually operator 2 and 3 might accept that operator 1 doesn't pay anything and so has a null cost allocation. This, of course, is an extreme case, but it's just a measure of the fact that in this case, for this tariff, the profit increase for the other two operators will be so high that still they could be willing to pay this all the costs also for operator 1 in order to achieve this higher profit. And why operator 1? Because as we see, it's got the smaller bandwidth and number of users in the region, and so the cost related to operator 1 has got the minor impact on the total cost. So it's almost negligible for the other two operators. So in order to conclude, we proposed a novel scheme for evaluating incentives for operator to cooperate by using a collisional game theory approach. We consider the case of 3 coexisting MNOs in 2 scenarios, one with equal bandwidth and market share, the other one with the bandwidth owned by the operators proportional to the market share. The incentives we consider are modeled in terms of offer data rate to the users and profit gain to the operators. And the results can be summarized this way. Cooperation is always beneficial to both users and operators. And in the coalition choice, pricing and the MNO size is very important. And the market share can be considered as a fair solution and feasible, as it always belongs to the core region. In the future work, we would like to extend this work to the general case of N operators. Thanks for your attention.